We're going to start our new unit today, and our new unit is called Simple Harmonic Motion and Waves. Now, the first part of the unit, Simple Harmonic Motion, may seem at first to have not a whole lot to do with waves, especially once we define it. You're going to look at it and say, what does that have to do with waves? Once we get into the waves unit, you'll see a very clear connection between what we call simple harmonic motion and waves. What is simple harmonic motion, first of all? Well, we talked about this just a little bit back in our dynamics unit. We said that simple harmonic motion is motion in which the restoring force is proportional to the displacement. Motion in which the restoring force is proportional to the displacement. In other words, F, the restoring force, is equal to something times x. F is equal to a constant times F. In other words, K times x. Remember doing that back in Unit 2, our dynamics unit? We said K is equal to F over x. We call that Hooke's law. That really is just the definition for simple harmonic motion. Motion in which the force is directly related to the displacement. The bigger the displacement, the bigger the force. Now, strictly speaking, we should have a negative value in front of that. We didn't talk about that back in Unit 2. We just made it F is equal to Kx. But there should be a negative in front of it because the negative gives us a force that's opposite to the direction of the displacement. In other words, if you pull a spring to the right, which way is the restoring force going to act? Which way is it pulling it back? To the left. If you pull the spring to the left, which way is it pulling it back? To the right. So whatever direction the displacement is, the restoring force is always in the opposite direction. On your data sheet, the equation is listed like this. F is equal to negative Kx. Sometimes you will use, however, the positive version of that. F is equal to positive Kx. F is equal to negative Kx really is the definition of simple harmonic motion, motion in which the restoring force is proportional to the displacement. F is equal to Kx would stand for the applied force, how hard I'm pulling. If I pull with the value of F, it's going to be in the same direction as the displacement. It's going to pull back with a value of F, or the negative value of F, the restoring force. That's the real definition of simple harmonic motion, but in the end, we think of simple harmonic motion, usually at least, quite simply as motion that repeats itself. Back and forth, back and forth, back and forth. The swinging ship at West Edmonton Mall on your field trip is simple harmonic motion, motion that repeats itself. The ship goes back and forth, back and forth, back and forth. In fact, any pendulum, including my set of keys up here, as I pull it back and let it go back and forth, back and forth, back and forth, that's simple harmonic motion. Another example of simple harmonic motion would be a spring. If you pull a spring back and then let it go, it vibrates back and forth, back and forth, back and forth very quickly. Now, there's a lot of damping in that spring, which means that the vibration of the spring dies out fairly quickly. But as it's vibrating, as long as it remains vibrating, then it's still going to be simple harmonic motion, motion that repeats itself, motion in which the restoring force is proportional to the displacement. So we're going to say some examples. The pendulum, the spring or elastic. Remember when we used this equation before, F is equal to Kx, Hooke's law? We used it in the context of springs, right? And we were finding the spring potential energy. We needed to find the spring constant. We were able to find the spring constant by rearranging that equation to get K. A couple terms that you've seen before in our circular motion unit. Frequency, if you remember that term from our circular motion unit, it was the number of revolutions per unit time. Well, we're not talking about revolutions now, we're talking about cycles back and forth, back and forth. So we're going to change the definition ever so slightly to the number of cycles per unit time. If we're talking about circular motion, one cycle is one complete revolution. If we're talking about the pendulum, one cycle would be from the start back to the start. If we're talking about a spring, one cycle would be from when it's stretched to when it's compressed, and then back again to when it's stretched to the point where it was in the beginning. The number of cycles per unit time. we can write down F is equal to the number of cycles over the time. Remember before we said it was the number of revolutions over the time. Same thing, really. The period given by the symbol capital T is the time for one revolution. Not for one revolution, I shouldn't say that. The time for one cycle, right? One complete cycle. And the equation for that one would be big T is equal to time over the number of cycles. There's an equation that relates period to frequency. What do you think it is? T is equal to 1 over F. Exactly the same as it was when we were dealing with circular motion. T is equal to 1 over F. Let's put all this stuff together that most of which we've seen before in previous units, whether it be our dynamics unit, Hooke's law, or whether it be our circular motion unit, frequency and period. Let's solve a problem on page 345. This one says, what is the frequency of an automobile engine which the pistons oscillate with a period of 0.0625 seconds? So this is not an object moving in a circle and us having to solve for the frequency or the period. This is objects moving up and down, up and down, up and down. Is that simple harmonic motion? It's a motion that repeats itself? Sure it is. It's a motion that repeats itself. And if you looked more closely at it, you would find, at least it would be very, very close to this, the restoring force acting on the piston would be directly proportional or directly related to the displacement. The bigger the displacement, the bigger the restoring force. Let's solve for the frequency of this engine now. We are given the period, T is equal to 0.0625 seconds, and we're looking for the frequency. What are we going to do to find frequency? Yeah, let's say T is equal to 1 over F. Let's rearrange that. F is equal to 1 over T. 1 over 0.0625. Pretty easy question, right? What do we get when we do the division there? What is it? 16? 16 cycles per second. We're not going to say revolutions per second anymore. We're going to say cycles per second. But it's still okay to say hertz, because 1 hertz is going to represent 1 cycle per second. So it's a pretty easy question. Let's take a look at a couple of pretty easy questions that go along with this pretty easy question. See what you can do with those two questions on page 345 over the next 1 minute or so. We're good with these questions? All right, let's move on. Let's talk about specifically one form of simple harmonic motion, that being the pendulum. This is what's going to help you to solve the questions that appear on your West Edmonton Mall assignment where you're looking at the small swinging ship. A pendulum, first of all, is quite simply a device consisting of a string and a bob. We put that in quotation marks. A bob, just the object at the end of the string, hanging from the string that swings back and forth, back and forth, back and forth. And of course, the period of that pendulum is the time that it takes the pendulum bob to swing from one spot through a complete cycle back to where it started. So we're not talking about the pendulum going from here over to here. That's not one complete cycle. One complete cycle is that pendulum going from here over to here and then back to here again. It's got to go back to where it started to be one complete cycle. All right, what do you think affects the period of a pendulum? What variables do you think would affect how long it takes the pendulum to go back and forth? Give me one. The speed? Well, speed's going to change, right? Speed's going to change as the pendulum is at its highest position. We'll say its maximum amplitude. It's going to be 0, right? And then it's going to speed up, speed up, speed up. It's going to reach its maximum speed. Then it's going to slow down, slow down, slow down, and then it's going to stop, and then it's going to reverse directions. So let's not say the speed, because the speed is changing. It's pretty. Acceleration is going to be gravity, right? 9.81. Okay. So let's say, is that what you mean, the acceleration of gravity? Yeah, at the ride at West Edmonton Mall, it's a little bit of a what we're going to do is a bit of an approximation because there actually is, you actually are being pulled upwards and pushed downwards as well. It's not a perfect pendulum. It's not perfect simple harmonic motion. Let's assume perfect simple harmonic motion here, where it's just a straightforward pendulum, the keys at the end of the string. Okay. Let's write down that as one of our hypotheses in terms of what's going to affect the period of the pendulum, the acceleration due to gravity. What else? I'm sorry? Okay, so you're saying two things. The radius, it's kind of a circle, right? So the radius of the circle, let's call that the length of the pendulum. Okay. The length of the pendulum. What else did you say, sorry? Okay, so the mass, you mean the mass, I think? The mass on the end of it? The mass of the pendulum bob. What else? Length, gravity, the mass of the pendulum. Don't cheat, Chase. Somebody that hasn't cheated, tell me what else you think affects it. What about how high I started from? Its initial position. Okay, let's call it X. You know what? Let's call it theta, the angle. Okay, we measure the angle from the equilibrium position or from its natural up and down position. That's going to be related clearly to its displacement, how far it's initially dropped from. Let's try a couple of these now. We can't try gravity. In fact, I'll tell you right now that gravity does affect it. The acceleration of gravity affects it. The period of a pendulum on the moon will be different than the period of the pendulum on Earth. The period of a pendulum on the top of Mount Everest, for that matter, will be different than the period of a pendulum in Vancouver. Not a great deal different, but it will be a little bit different because the acceleration of gravity or the gravitational field strength does matter. What about the angle? Let's vote on that one. How many people think the angle or the initial displacement is going to affect the period of the pendulum? In other words, start a pendulum from this position versus starting a pendulum from this position. Who thinks that will affect the period of the pendulum? Hands up if you think it will. Okay, here's what I want you to do. I'm going to take my keys here, my standby pendulum here, and I'm going to let them swing back and forth in simple harmonic motion. What I want you to do is kind of in your head, not with a stopwatch or your iPhone or whatever, but just kind of in your head, time it. Start, stop. Start, stop. I'll tell you, I'll say start and I'll say stop. I want you to tell me in two different scenarios, when we change the angle, change the initial position, if the time is the same. Now, you're not going to be able to tell exactly whether the time is the same by just using your head, but you're going to be pretty close to it. If I say start, stop, and in the next trial I say start, stop, well then clearly there was a difference in time. Clearly in that case, the initial displacement affected the period of the pendulum. Okay? Let's go back and forth here. Again, I'll say start, stop. You're going to time this roughly in your head. If you want to use an iPhone to time it, go ahead. Okay? Start, stop. Start, stop. Start, stop. So we're dealing with an angle in all three of those cases of about 45 degrees there. You see that? I haven't measured the angle, so I don't know if it's exactly 45. Maybe it's 43. Maybe it's 46. I don't know. It doesn't matter. Okay, it's pretty close to 45 degrees. Start, stop. Start, stop. Start, stop. Now let's go a much smaller angle. Let's say maybe 10 degrees. And clearly that's a much smaller initial position, a much smaller angle. Let's see if that's going to affect the period of the pendulum. Start, stop. Start, stop. Start, stop. Let's go back up to 45. Start, stop. Start, stop. Did it matter? Did the initial displacement matter? The initial displacement didn't matter, which is kind of counterintuitive. You would think the further it has to go, the longer it's going to take, right? Anybody explain to me why it doesn't? Anybody explain to me why, when I drop it from an angle of 10 degrees, we're going to have the same period as when I drop it from an angle of 45 degrees? It's a little bit counterintuitive. Most of us wouldn't have predicted that, but now that we know it's the case, maybe we have a good justification as to why it actually happens. Megan? Good, good. It doesn't have as much time to speed up at an angle of 10 degrees. It's got a lot less distance to travel, but it's going a lot slower to travel that shorter distance. And it's going a lot slower because it doesn't have as much time to accelerate. So when you drop it from 45, yeah, it's got further to go. Start, stop. But because it has more distance to accelerate, it's going to get to a bigger speed. And therefore, you're going to cover a bigger distance, bigger speed, certain amount of time. When you're at 10 degrees, it accelerates a lot less. Start, stop. It's got a lot less distance to travel, but it's going a lot slower, so it's still going to end up taking the same amount of time as when I dropped it from 45 degrees. The angle, oddly enough, doesn't matter. That's actually not quite true. We say that, strictly speaking, the angle does matter. It does. But to a good approximation, at relatively small angles, say below about 40, 45 degrees, the difference in the period is so small that we don't pay any attention to it. There is a small difference. And especially when you go to big angles of 60, 70, 80 degrees, there's a measurable difference, a noticeable difference in the period of the pendulum. But below 40, 45 degrees, the difference in the period of the pendulum is so small that we don't pay any attention to it. We just say that the angle, when you're below that 40, 45 degrees, just doesn't matter. Let's try the length of the pendulum now. Okay? My pendulum right now is about, I would say it's about 40 centimeters long here. Okay, you see the string is about 40 centimeters long. Okay, once again, we'll go to an angle of about 45 degrees. Start, stop. Start, stop. Start, stop. Let's reduce the length of that pendulum now by about a factor of 2. Okay, so now it's much shorter. Now we're at an angle of 45 degrees again. Let's drop it. Let's time it again in our head, and let's see if we have the same period or a different period. How many people think the length of it will affect it? Okay. Let's go 40 centimeters again. Start, stop. Start, stop. Let's cut it to about 20 centimeters. Start, stop. Start, stop. Start, stop. Did the period matter? Or sorry, did the length of it matter? Yes, it did. So the length of it matters. The acceleration due to gravity matters. The angle or the initial position doesn't matter. Let's try one more thing. Let's try the mass of it. Okay, right now, I'm not sure what the mass of this set of keys is. Okay, obviously it's a certain value, maybe 100 grams. Okay, with the keys on the end of this pendulum. Start, stop. Start, stop. Let's add another mass onto the end of it. This mass that we have up here is a 200 gram mass. So it's going to change the mass of it quite dramatically. We're going to increase it by a factor of about 3. Hanging on the end of it here. We'll pull it up to an angle of 45 degrees again. How many people think this one's going to affect it? Bigger mass. Okay? With the mass, start, stop. Start, stop. Start, stop. Without the mass, start, stop. Start, stop. Did it matter? The mass doesn't matter. Now, this is one of those ones that might be a bit counterintuitive as well before it happens, but once we see that it doesn't matter, we could probably come up with a pretty good explanation as to why it doesn't matter. Anybody suggest to me why the mass doesn't matter? That's the big one right there, the force of gravity. If you drop something straight down, the rate of acceleration would be 9.81 meters per second squared, regardless of what the mass is, right? So if we're dropping something and it's moving in a circular motion because of simple harmonic motion, because of the pendulum, ultimately it's still being pulled down by gravity. And the mass, it doesn't affect what the acceleration is because of gravity. It's only the mass of the Earth, the mass of the producer that affects that. So the mass of the experiencer isn't going to have any bearing on the acceleration as it falls straight down, nor is it going to have any bearing on the acceleration as it goes in that pendulum path. So the mass isn't going to matter. The only two things that affect the period of the pendulum, in fact, are, at least at angles below about 45 degrees, the gravitational field strength and the length of the pendulum. Now, unfortunately, they both affect the period of the pendulum in an odd sort of way. The period of the pendulum is equal to t, the period, which is equal to 2 pi times the square root of L over G. It's a little bit of an ugly equation. What's even uglier than the equation that you see up on the board right now is when you have to rearrange it to solve for one of those variables. Maybe you have to rearrange it to solve for g or rearrange it to solve for L. We don't usually do this when we introduce a new equation, but because this one is particularly ugly rearranging, we're going to rearrange it to solve for all three of the variables that we can solve for here. T, which we've already got, we're going to rearrange it to solve for L, and we're going to rearrange it to solve for G, just so that you've seen it done once at least before you have to do it yourself. Let's say we want to rearrange this equation to solve for L. What do we get rid of first? Let's get rid of the 2 pi first, the 2 and the pi. Let's take the 2 pi over by division. Yeah, so it's going to be t over 2 pi is equal to the square root of L over G. We're still not done. What do we get rid of next? Square root. So it's going to be t over 2 pi. What do we do to get rid of the square root? Square both sides. So t over 2 pi squared is equal to L over G. Finally, we want to solve for L, then we're going to get rid of the G. How do we get rid of the G? We're going to multiply it. So it's going to be G times t over 2 pi squared equals L. It's an odd-looking equation, but it works to solve for L. Let's say now that we want to rearrange to solve for G. What I'd like you to do at this point to solve for G is do exactly what Tanner just suggested, I think, and that is do exactly the same thing as we've just done, and then go one more step. We've solved for L. We've got L is equal to G times t over 2 pi squared. Let's take the t over 2 pi squared over to the other side by dividing. So it becomes L over t over 2 pi brackets squared equals G. You think the first one looked ugly? Think this one looks ugly? This one's even worse. L over t over 2 pi squared is equal to G. Does the rearranging of this equation to take both forms here, L and G, make sense? Be prepared to do that, okay? Be prepared for that. Let's take a look at a problem that goes with this now. What is the gravitational field strength? Right away, we have to solve for something other than T, the period, the gravitational field strength here. What is the gravitational field strength at the top of Mount Everest at an altitude of 8954 meters? That would be above the surface of the Earth, above sea level, if a pendulum with a length of 1 meter has a period of 2.01 seconds. We want to find G. We've got the distance, we've got the period, 2.01 seconds. We've got the length of the pendulum, 1.00 meters. And we've got the distance above the Earth, the altitude. Is that going to matter here? No. I mean, the altitude affects the period, but we're accounting for the altitude already with the period of 2.01 seconds. When we plug this into our equation for the period of a pendulum, the altitude isn't going to go in there anywhere. Let's write down that equation and rearrange it to take the form that we need to take here. T is equal to 2 pi square root L over G. Let's solve for G. Take the 2 pi down by dividing. Let's take the square root over by squaring. It becomes T over 2 pi squared equals L over G. Let's take the G up by multiplying, and then the T over 2 pi down by dividing. And remember, we end up getting this equation. G is equal to L over T over 2 pi squared. Let's plug our numbers in now. L is 1.00 meters. Divided by 2.01 seconds over 2 pi. Let's bracket that and square it. Let's do that on our calculator now to make sure that we can do that on our calculator. Let's do the bottom first. Okay, let's do what's inside the brackets first. Let's go 2.01, divide it by, and then let's get some brackets there, 2 times pi, end brackets. Now I've got what's inside the brackets. Let's square that now. This is what's on the bottom now, 1 over this. Now let's flip that over. If we want to take 1 over that, then we'll go 0.102 x to the minus 1 gives me 9.77. And the units would be meters per second squared, or we know a new set of units that we can use for this now. What is it? Newtons per kilograms would work here as well. So 9.77. On the surface of the Earth at the equator, it's somewhere around 9.8, 9.81. Top of Mount Everest, it's 9.77. Is it dramatically different? No. But is it different? Yeah, it's different, and it's measurably different. If you're able to find the period of a pendulum wherever you are, okay, wherever you are on the face of the Earth, if you find the period of the pendulum fairly accurately, then you can find the gravitational field strength also fairly accurately. Let's take a look at these 3 questions now. They'll go along with the practice problem that we just did. Page 379, let's see what we can do with these. We'll give you a little bit more than a minute to solve these ones because they're a little bit more challenging than the last set that I gave you. Any issues with these 3 questions before we move on? All right, I want to do one more thing today. It's a phenomenon called the resonance that I want to describe. First, I want to define a term that we call resonant frequency. Every different object, everything on Earth has a certain natural frequency at which it wants to vibrate. That natural frequency at which it wants to vibrate is called the resonant frequency. If you hit your hand against the wall, you hear a sound. That's the sound of the wall vibrating, the resonant frequency of the wall. If you take a meter stick and you put it against the desk and you give that meter stick a flick, you're going to hear a sound. That's because the meter stick has a certain natural or resonant frequency at which it wants to vibrate. If you pluck a guitar string, it will vibrate with a certain natural or resonant frequency, and that's the sound that you hear. If you hit a drum, okay, with a drumstick, it's going to make a certain frequency, a certain sound. That's the sound of the natural frequency, the resonant frequency of that drumstick. Sometimes, driving down the highway in your old, 1980s car, you get to 97 kilometers per hour or whatever speed. Every car is a little bit different, right? And something starts vibrating. You ever experienced that in your car or somebody else's car? But then you get up to 103 and it's not vibrating anymore? It only vibrates at a particular speed? Well, if it's vibrating at its natural frequency. Whatever object that's vibrating is vibrating when the car hits its natural or resonant frequency. Every object has a natural or resonant frequency. So we're going to say the resonant frequency is the natural frequency at which an object wants to vibrate. We're using the term wants, obviously, loosely, because we're not talking about a real desire to vibrate. It's just a natural frequency at which something will vibrate given the opportunity. Go ahead. Everything would vibrate in space, yeah. Yeah, the resonant frequency is not affected by gravity. So if the resonant frequency of this meter stick is 100 hertz, when I flick it against the desk, if I flicked it against the desk in space, it would also vibrate at 100 hertz. Now, if you're in the middle of space and you do that, you wouldn't hear the sound that we just heard because sound requires a medium to travel through. But it would still vibrate back and forth at exactly the same frequency. No. The question, if you didn't hear that, was if you just let it go in space, would it vibrate at that frequency? No. It has to be given a disturbance. It has to be hit, or it has to be disturbed in some way to cause it to vibrate at its natural frequency. It's not going to just happen by just leaving it to sit there, even in the absence of gravity. It's a good question. Yeah. Brendan, do you have a question? Okay. Yeah, but it needs to be given the opportunity to vibrate. Yeah, it wants to vibrate at that frequency, but it's not just going to happen without being prompted to do so. When my pendulum, my keys, this is the perfect example of resonant frequency, because we can predict exactly what the resonant frequency of these keys are. The keys equal to 2 pi squared out of the key. That's a little 1 over. So we can predict very easily what the resonant frequency and the natural frequency of these keys are that we swing back and forth. We're not going to do it now. Right now these keys are just sitting there. Well, I have to disturb them somehow. I have to prompt them to vibrate on the frequency. I do that by lifting off like this, and then I have to go. If I prompt them to vibrate on the natural frequency, then I'll do it. But they're not going to pursue it anyway. Yes, if there's no resistance or friction, we just keep going. But in the end, there always is resistance or friction. Yes. I think that is correct. If there's resistance on this pendulum as it goes back and forth, would it still vibrate the same frequency? Effectively, yes. Yep. No. Well, frequency is the sound. It's manifested as the sound. Frequency is the number of cycles per second. So it's like a different music. It vibrates back and forth at a certain number of cycles per second. Now, that frequency manifests itself as a sound. I'm going to hear that sound and the music vibrating back and forth. Even if that sound's not there because of that, or because it's in space, and there's no sound that's transferred, whatever, then it's still vibrating at that same frequency. It just doesn't manifest itself as a sound. Like the pendulum swings back and forth. We don't really hear a sound for that. But there's still a resonant frequency. There's still a frequency. Now, resonance, to differentiate resonant frequency from resonance, resonance is the phenomenon whereby an object can start vibrating out of control if a natural frequency of the resonant frequency is matched. I'll explain that in just a second. I'll just write this down, and then I'll explain what I'm doing. Phenomenon whereby an object's amplitude of vibration increases as a disturbance. Let me just finish this up. As a disturbance is being applied at the object's natural frequency. What do I mean by that? Well, let's say the natural frequency of these keys, let's make it a swing set. Which of these keys is a swing set? Okay, let's say the natural frequency of these keys is 2 cycles per second. You guys know this if you've ever put somebody on a swing set, and every single one of you has done this before. You put someone on the swing set, you want that vibration to grow. You want the amplitude of disturbance to grow. So what do? You push it. You apply a disturbance at the natural frequency of the swing set. You're not going to apply a disturbance like this, push, at random time intervals. When your little brother or sister is going back and forth in the swing set, when do you push? You push now. If you want to get them vibrating more and more and more, you apply the force at the natural frequency of that swing set. That causes the disturbance to grow. Now, sometimes you can cause the disturbance to grow to the point where something breaks. I'll show you a video tomorrow of a bridge. It was in Washington State 50, 60 years ago, called the Tacoma Narrows Bridge. Literally, this bridge was a few months old. It started vibrating in the wind because the natural frequency of the bridge was matched by the frequency of the wind. The bridge actually collapsed. I'll show you a video of that tomorrow, okay? No homework tonight. We'll finish this up tomorrow, and then we'll give you some practice problems on that.